Hello everyone, my name's Logan and welcome back to the lecture hall. For today's UCI Math 2B calculus video, we are covering section 11.4, limit comparison tests, because fuck Trig's son. So we begin this video with a theorem. I guess it's a two-part theorem, and it states that suppose the sum of a to b and the sum of b to, the sum of an and the sum of bn are series with positive terms. If bn is convergent and an is less than, or the sequence an is less than or equal to bn for all n in the sequence, so that's every single term in the sequence, then an is also convergent. Now we have the second portion that says if the sum of bn is divergent and an is greater than or equal to all bn, so all b in the sequence bn, then an is also divergent. And so, what does this mean? Well, essentially, we're just comparing these two sequences. If one series converges and it's less, and then there's another series that is less than or equal to for all the terms, then it obviously makes sense that it has to converge. While if there's a series that diverges and there's an even bigger series on it, it makes sense that that diverges as well. How can we use the limit comparison test? Well, here, what if we had the series, the sum from 1 to infinity of 1 over 2 to the n plus 1? Well, we don't actually know how to deal with a series like this yet, and we see 1 over 2 to the n plus 1. Well, it almost looks like a power series, and we can actually compare it to a power series. If we take 1 over 2 to the n, well, 1 over 2 to the n is going to be greater than or equal to, well, it's actually going to be greater than 1 over 2 to the n plus 1 for all n. For all n. And then we're like, okay, so we have a smaller series that we know is convergent. We know 1 over 2 to the n is convergent, and we know that 1 over 2 to the n plus 1 is less than or equal to, well, it's going to be less than, for every single term in the sequence of 1 over 2 to the n and 1 over 2 to the n plus 1. So we can then say, well, this 1 over 2 to the n plus 1 is convergent by the limit comparison test. Because we know 1 over 2 to the n is convergent, and 1 over 2 to the n is greater than every single term in 1 over 2 to the n plus 1, so 1 over 2 to the n plus 1 has to be convergent by the limit comparison test. Now we have the limit comparison test, and it states, suppose that the sum from 1 to infinity of an and the sum from 1 to infinity of bn are series with positive terms. If the limit as n approaches infinity of an, the sequence portion of it, over bn, just the sequence portion, equals some constant c, then both converge or diverge. So, essentially, what this means is if we put one sequence over another sequence and they equal a constant, then both will either converge, or both series will either converge or diverge. So if we get something like infinity or something over 0, then we can know that one of the sequences diverges and then the other converges. While here, if it equals a constant, then both do the same thing. They either both converge or both diverge. To see the limit comparison test in practice, we have the series, the sum from 1 to infinity of 2 to the n squared plus 3n all over the square root of 5 plus n to the 5th. And we're like, holy fucking shit, that's an ugly series. And we're like, okay, well, we know we have the limit comparison test. So let's just take the dominant terms from the numerator and denominator. What do you mean by dominant terms? Well, the terms that have the biggest exponents. So let's just take 2n squared over, well, the square root of n to the 5th, which is n to the 5 halves. Well, then, if we simplify that down a little bit, because we can then be like, okay, well, we'll call this Bn. And we can say, okay, well, this is 2 over n to the 1/2. And now we're like, okay, well, cool, but where do we get the limit comparison test? Well, we get it by just comparing the two. What? It's almost like this video is called comparing them. Well, so we take it and we do, okay, well, we need the limit of a to the n over b to the n. We're going to say this is a sub n and this is b sub n. Well, so then we're going to take the limit of, as n approaches infinity, of 2n squared plus 3n over the square root of 5 plus n to the 5th, divided by 2 over n to the 1/2, or times n to the 1/2 over 2. And so this will come out to be 2 to the n to the 5/2 plus 3n over square root of 2 times 5 plus n to the 5. And we're like, okay, cool, but this doesn't help us, does it? Well, actually, it does, because with limits, we can manipulate these equations and we don't actually have to deal with the whole portion of a limit, because limits go to infinity, so you only have to focus on the dominant terms. So we can be like, okay, well, we look at the dominant terms, well, that's going to be 2 to the n to the 5 over 2. And then we're going to look at, well, 2 times, well, the dominant term here is 5, n to the 5 to the 1/2, right, because it's square rooted. So then we see, well, this is just like the limit as n approaches infinity of 2 to the n to the 5/2 plus blah, 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 over 2 times n to the 5/2 plus blah, blah, blah. And when the powers match, or the dominant powers match, you just take the ratio of their constants, which is going to be 2 over 2, which is going to equal 1. We're like, okay, what the fuck? Why do we even do that? We found out the limit's 1. Well, that means that these series either both converge or both diverge. And now we're going to take a quick look back at 2 over n to the 1/2. Well, from our power series, we know that if the power is greater than 1, then the series converge, but n to the 1/2 is less than 1, so the series diverges. This 2 over n to the 1/2. So then that means this series, the sum from 2 times n squared plus 3n over the square root of 5 plus n to the 5th will also diverge. So that's all these are the only two things that we had to cover in the lecture portion of the video. Let's transition to some practice problems. To begin our practice problems, we are starting with number 8 from our textbook, and this is the sum from 1 to infinity of 6 to the n over 5 to the n minus 1, and we're like, fuck, we don't know. And it's got this minus 1, and it almost looks like a power series. Well, we can just use the comparison tests. And we're going to use the first comparison test, which compares the sequences with one another, and we're going to notice 6 over 5 to the n minus 1 is greater than or equal to what for every sequence? Well, it's going to be, if we have 6 to the n over 5 to the n, which is equal to 6 over 5 to the n, we know that this 6 to the n over 5 to the n minus 1 is going to be greater than or equal to all these terms. And then we look at 6 over 5 to the n and we're like, oh, that's a power series. Or a geometric series, my apologies. Whoa, whoa, whoa. And we're like, oh, okay, or a geometric sequence. And we're like, okay, well, we know this is going to diverge because it's greater than 1. And what do I say is greater than 1? Well, 6 over 5 is greater than 1. And our r, in the terms of r to the n, our r has to be less than 1 for it to converge. So then we're like, oh, okay, well, this diverges. This is greater than or equal to for every single term in the series, or sequence. So this function, or this series, diverges. Now if we have the series, the sum from 1 to n of 1 over n to the power n, we're like, oh, yikes, that's ugly. That's like really ugly. N to an n, so that's a term to a term, and the term is changing every time. Well, how do we figure this out? Well, we got to kind of think on it, and we're like, okay, we want to compare. We want to compare, we want to compare. What can we compare it to? Well, n to the n, well, that means it's using powers, so then we could compare it to 1 over n squared, right? Because if we plug in 1 for 1 over 1 squared, that's still 1. And then if we plug in 2, that's 1 over 2 squared, which is equal to 1 over 2 to the 2, if it was in 1 over n to the n. And then, if we do 1 over 3 to the 3, well, that's going to be less than 1 over 3 squared if we had 1 over n squared. So we compare 1 over n squared, and we're like, okay, we have 1 over n squared. And it turns out that 1 over n squared is going to be greater than or equal to every single term in 1 over n to the n. What else do we know? Well, 1 over n squared is a power series, and if our power is greater, that would be this 2, is greater than 1, which 2 is greater than 1, then 1 over n to that power converges. So, because 1 over n squared converges, and it is greater than or equal to every single term in 1 over n to the n, then 1 over n to the n converges. Now we have a really ugly one, and we're also going to use the limit comparison test, because I've used the other comparison test for the other two, so we might as well use the limit comparison test here. We have this series, the sum from 1 to n, or 1 to infinity, of n plus 2 over n plus 1 cubed. So, what do for limit comparison? Well, we take the dominant terms from each series, so we have n, and then if we would to do this math out, we could with Pascal's triangle, and then we know this term is going to be n cubed. So we're going to say b to the n is equal to n over n cubed, which is equal to 1 over n squared. We know that, that's simple algebra. So then we're like, okay, let's compare these two. So we do, we take the limit of their division, of their quotient. What? We take the limit of their quotient, not we take the limit of their division. What the fuck, Logan? So then we have n plus 1 cubed, and we continue, and we multiply. Well, what do we multiply? We multiply by 1 over b, because we are dividing by b, so then we flip b to the n, b sub n, and that's going to be n squared over 1. And if we do this out, this equals n cubed plus 2n squared over, well, n plus 1 cubed, which is going to be n cubed plus other stuff. We don't even need to write it down. We know how to find it. We've fucking multiplied polynomials every day in algebra. But we don't have to do that right now, because all we need is our dominant term. And then we're like, okay, where do we go from here? Well, if we take the limit of as n approaches infinity, and we have an n cubed plus blah 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 over n cubed plus blah blah blah, then we're like, okay, well, we take the dominant terms, their exponents are the exact same. So then, we're like, okay, their exponents are the exact same, so we take the ratio of the denominator, or numerator over the denominator, and we're like, okay, well, that's 1 over 1, so then that means our limit is equal to 1. And we're like, okay, well, we know from the last problem that 1 over n squared converges, and if our limit for the limit comparison test equals a constant, which 1 is a constant, then both follow the same rule of convergence or divergence. 1 over n squared converges, so n plus 2 over n plus 1 cubed does what? Converges. You knew that. Fuck yeah. Okay, well, that is all I wanted to cover in the video today. As always, my name was Logan. Thanks for watching. Have a great day. Showing you my nuts.